the factory that turns gas into food. So you want to own a fertilizer factory. Imagine owning an industrial complex that produces millions of tons of fertilizer every year. Pipes run across the facility. Compressors operate around the clock. Huge reactors convert gases into chemical. Storage tanks hold thousands of tons of product. And trucks, trains, and ships continuously move fertilizer toward farms around the world. At first, the business looks almost unbeatable because fertilizer isn't a luxury product. Farmers need it to grow crops. Corn needs it. Wheat needs it. Rice needs it. Sugarcane needs it. Vegetables need it. And as the world's population grows, agricultural production needs to keep up. But there is a problem. Fertilizer manufacturing is one of the most energy-intensive businesses in the world. The factory requires enormous amounts of natural gas, electricity, water, specialized equipment, and capital. And unlike many consumer products, fertilizer prices can swing dramatically depending on energy markets, crop prices, weather, geopolitics, and global supply. So the real question isn't how much fertilizer a factory can produce. It's how much money remains after paying for the gas, electricity, labor, maintenance, transportation, financing, and everything else required to keep the plant operating. To understand that, let's build the economics of a large-scale fertilizer factory from the ground up. Which fertilizer factory are you buying? There are many types of fertilizer: phosphate fertilizer, potash fertilizer, nitrogen fertilizers, and blended products. For this model, imagine we're buying a large nitrogen fertilizer factory producing urea. Urea is one of the world's most widely used nitrogen fertilizers, and its production starts with something surprisingly simple: natural gas. The gas isn't just burned for energy. It is also used as a feedstock to produce hydrogen, which eventually becomes part of the ammonia used to manufacture urea. That makes natural gas one of the most important economic variables in the entire business. Imagine our factory has the capacity to produce approximately 1 million tons of urea per year. That's a massive operation. The facility needs ammonia production units, urea reactors, compressors, boilers, cooling systems, storage facilities, packaging equipment, laboratories, pipelines, rail connections, and loading infrastructure. A fertilizer factory isn't simply producing bags of powder. It's converting energy and raw materials into a product that ultimately helps produce food. And doing that at massive scale requires enormous capital, the first $1 billion. Now imagine building a modern large-scale fertilizer complex requires approximately $1 billion in total capital. The actual cost can vary significantly depending on location, technology, capacity, infrastructure, energy prices, environmental requirements, and whether ammonia and urea production are integrated. But $1 billion gives us a useful model. That money goes into reactors, compressors, pipelines, storage, power systems, cooling systems, processing equipment, buildings, rail infrastructure, environmental controls, and installation. But construction isn't the only capital requirement. The factory also needs working capital. Before the first fertilizer shipment generates cash, the company may already have millions of dollars tied up in raw materials, spare parts, inventory, wages, transportation, and customer receivables. Suppose the owner needs another $100 million in working capital. Now, approximately $1.1 billion is tied up in the business, and that capital has an economic cost. If the owner expects an 8% return on $1 billion, that's roughly $80 million per year that the business needs to justify its capital investment. A fertilizer factory doesn't become profitable simply because it produces millions of tons. Those millions of tons have to generate enough cash to justify the billions invested in the factory. From natural gas to fertilizer. Now the manufacturing process begins. Natural gas enters the plant. The gas is processed to create hydrogen-rich synthesis gas. That hydrogen is then combined with nitrogen from the air to produce ammonia. The ammonia becomes the foundation for nitrogen fertilizer production. Inside the urea plant, ammonia reacts with carbon dioxide under high pressure and temperature. The resulting chemical mixture is processed until urea is formed. The urea is then concentrated and converted into small solid granules or prills. Those granules are cooled, screened, stored, and eventually loaded for shipment. The final product may look simple, a bag filled with white fertilizer granules. But behind that bag is a highly complex chemical process. The remarkable part isn't that fertilizer can be produced. It's that a factory can continuously transform natural gas, air, and water into millions of tons of agricultural nutrients, and every stage consumes money. The natural gas problem. Now we reach the biggest economic issue: natural gas. For many nitrogen fertilizer plants, gas is both a feedstock and an energy source. That means a change in gas prices can directly affect production economics. Imagine our factory spends approximately $250 million per year on natural gas. Now imagine gas prices increase by 30%. The factory could suddenly face another $75 million in annual costs. The equipment hasn't changed. The workforce hasn't changed. The amount of fertilizer produced hasn't changed, but the cost of making every ton has increased, and the factory may not be able to immediately increase fertilizer prices enough to compensate. This is the fundamental fertilizer problem. The factory sells fertilizer, but one of its most important inputs is an energy commodity whose price can move independently of fertilizer prices. That creates enormous risk. A factory with access to cheap and reliable natural gas can have a major competitive advantage. A factory dependent on expensive gas can struggle even when fertilizer demand is strong. The cost inside every ton. Now let's build a simplified economic model. Suppose the factory produces 1 million tons of urea every year. Imagine the average selling price is approximately $350 per ton. That produces roughly $350 million in annual revenue. But the factory has to manufacture those million tons. Suppose natural gas and energy-related costs account for approximately $250 million. Labor, maintenance, chemicals, water, administration, insurance, and other operating costs might add another $60 million. That puts basic operating costs around $310 million. At $350 million in revenue, approximately $40 million remains before depreciation, financing, taxes, distribution, and other expenses. Suddenly, that billion-dollar factory doesn't look nearly as profitable. And this is where fertilizer economics become dangerous, because fertilizer prices can change dramatically. The fertilizer price cycle. Fertilizer demand is closely connected to agriculture. When crop prices are strong, farmers can afford to spend more on fertilizer. They may increase application rates. They may plant more acres. And fertilizer demand can rise. But when crop prices fall, farmers may cut costs. They may reduce fertilizer purchases. At the same time, new fertilizer capacity can enter the market. That can create excess supply. Prices fall. Imagine our factory's average selling price drops from $350 per ton to $280 per ton. At 1 million tons, revenue falls from $350 million to $280 million. That's a $70 million reduction in annual revenue. But many operating costs remain. The factory still needs gas. Workers still need to be paid. Equipment still needs maintenance. And the plant still needs to meet environmental requirements. When fertilizer prices fall, the factory doesn't suddenly become 20% cheaper to operate. Her revenue falls faster than many of the costs. That's what makes commodity manufacturing so dangerous. The capacity utilization shock. Now imagine demand weakens. The factory operates at only 70% capacity. Instead of producing 1 million tons, it produces approximately 700,000 tons. Some variable costs decline. Less gas is consumed. Less electricity is used. Less packaging is required. But the factory still exists. The reactors are still there. The compressors are still there. The storage tanks are still there. The workforce still has to maintain the facility. Insurance continues, maintenance continues, and the billion-dollar investment still needs to earn a return. A fertilizer factory doesn't just need to produce efficiently. It needs to synchronize production with the agricultural calendar. This is why utilization is critical. A factory operating near full capacity can spread fixed costs across enormous production volumes. A factory operating far below capacity can quickly become economically painful. The energy efficiency problem. Because energy is such a large part of fertilizer economics, efficiency becomes extremely valuable. Imagine two factories produce the same amount of urea. Factory A consumes significantly more natural gas per ton. Factory B uses modern equipment and consumes less. If natural gas prices rise, Factory A gets hit harder. Factory B has more protection. This is why fertilizer producers invest in modern reactors, compressors, heat recovery systems, process controls, and energy-efficient equipment. Even a small reduction in energy consumption per ton can create millions of dollars in annual savings at large scale. A fertilizer factory may sit in one country, but its economics can be controlled by events happening thousands of kilometers away. The transportation problem. Fertilizer is heavy. A factory producing 1 million tons per year needs serious logistics infrastructure: trucks, railways, ports, warehouses, storage terminals, and distribution networks. Some fertilizer may travel hundreds or thousands of kilometers before reaching farms. Transportation therefore becomes part of the product's economics. Imagine the factory produces fertilizer cheaply, but is located far away from its major customers. The company may save money during production, but lose the advantage through expensive logistics. A factory near natural gas supplies, rail infrastructure, ports, and major agricultural markets can have a significant competitive advantage. The storage problem. Fertilizer demand isn't perfectly consistent throughout the year. Farmers buy according to planting seasons. That creates peaks and valleys in demand. The factory, however, may prefer to operate continuously. Chemical plants are expensive to shut down and restart, so production may continue even when customers aren't buying at maximum levels. That creates inventory. Storage facilities become essential, but inventory costs money. Warehouses and storage yards require infrastructure. Product has to be protected, and capital becomes tied up in unsold fertilizer. Imagine the factory has $40 million worth of fertilizer sitting in storage. That is money that could otherwise be used for debt repayment, expansion, or other investments. When your product helps determine the cost of food, the government is never completely outside the business. The global supply problem. Fertilizer is a global commodity. A farmer doesn't necessarily care where the fertilizer was produced. They care about price, quality, availability, and delivery. That means a local factory can suddenly face competition from international suppliers. If another country has cheaper natural gas, lower production costs, or favorable export conditions, its fertilizer can enter the market at a lower price. This creates enormous pressure on high-cost producers, and because fertilizer is traded globally, geopolitical events can have major effects. Trade restrictions, export controls, shipping disruptions, energy shortages, currency movements, and changes in agricultural policy can all influence prices. The government problem. Fertilizer is politically important. Governments care about fertilizer prices because fertilizer affects farming costs, and farming costs affect food prices. That means governments may provide subsidies, control prices, support domestic production, restrict exports, reduce import duties, or intervene during periods of agricultural stress. For a fertilizer manufacturer, government policy can create both opportunities and risks. A subsidy can make domestic production more competitive. A price control can limit the manufacturer's ability to raise prices. An export restriction can reduce access to international markets. And a sudden policy change can completely alter the business model. The environmental cost. Modern fertilizer plants also face environmental challenges. Chemical production can generate emissions. The plant needs wastewater treatment, air pollution controls, monitoring systems, safety infrastructure, and systems to prevent leaks and accidental releases. These systems require capital, they require maintenance, and they require continuous monitoring. Imagine the factory needs to invest $50 million in environmental and safety upgrades. That investment may not directly increase fertilizer production, but without it, the factory may face regulatory problems, shutdowns, or significant liabilities. Environmental spending may not look like a revenue-generating investment, but in chemical manufacturing, it can be essential to keeping the factory open. The working capital trap. Now consider the money tied up inside the business. The factory needs raw materials. It needs spare parts. It has fertilizer inventory. It has customer receivables. And it may need to provide payment terms to distributors. Imagine the company has $100 million tied up across inventory and receivables. That money isn't sitting idle because the company is poorly managed. It's part of the normal working cycle, but it still has an opportunity cost. If fertilizer prices fall while the company is holding expensive inventory, the value of that inventory can decline. And if customers take longer to pay, the factory may need additional financing. A fertilizer factory can be profitable on paper and still face a cash flow problem if too much money becomes trapped inside inventory and unpaid invoices. Cash flow matters, especially in a commodity business. The ownership traps. The first trap is assuming fertilizer demand automatically means high profits. The second is underestimating natural gas prices. The third is building more capacity than the market needs. The fourth is ignoring energy efficiency. The fifth is underestimating maintenance. The sixth is choosing a poor location. The seventh is relying too heavily on government support. The eighth is allowing too much inventory to build up. The ninth is depending on a small number of customers. And the final trap is confusing revenue with profitability. A factory can produce 1 million tons of fertilizer and generate hundreds of millions in sales, while producing disappointing returns if energy and operating costs consume most of the revenue. The factory verdict. So what separates a profitable fertilizer factory from a billion-dollar industrial facility struggling to survive? Cheap and reliable energy, high utilization, efficient equipment, strong logistics, disciplined inventory management, reliable customers, and capital discipline. The smart owner doesn't simply ask how much fertilizer the factory can produce. They ask, how much will natural gas cost? How much fertilizer can the market absorb? What is the break-even price per ton? How much inventory will be required? How expensive will transportation be? How much will maintenance cost? And what happens if fertilizer prices fall by 20%? Those are the questions that determine whether the billion-dollar factory becomes a powerful cash-generating asset or a giant industrial liability. The real economics. From the outside, a fertilizer factory looks like a machine for turning natural gas into money. But underneath the pipes, reactors, tanks, and loading terminals is a much more fragile economic equation. The factory depends heavily on energy. It requires enormous capital. It operates continuously. It carries significant fixed costs. It depends on agricultural demand. And it competes in a global commodity market. When fertilizer prices are high and natural gas is cheap, the economics can be spectacular. A high-capacity factory can produce enormous amounts of fertilizer at relatively low cost per ton. Fixed costs are spread across millions of tons. Cash flow can surge, and the owner can generate returns that justify the enormous investment. But when natural gas prices rise while fertilizer prices fall, the equation can reverse quickly. The factory still needs gas. The equipment still needs maintenance. Workers still need to be paid. Environmental systems still need to operate. And the billion-dollar investment still needs to earn a return. A fertilizer factory doesn't make money because farmers need fertilizer. It makes money when the factory can produce fertilizer at a cost low enough to leave a meaningful margin after selling it into the global market. That's the real game. Energy efficiency matters, scale matters, location matters, utilization matters, and timing matters. So, is owning a fertilizer factory a license to print money? Not exactly. It's a massive industrial bet on agriculture, energy prices, commodity markets, transportation, government policy, and global food demand. If the factory has cheap natural gas, efficient equipment, strong logistics, high utilization, and reliable customers, the economics can be extremely attractive. But if energy prices explode, fertilizer prices collapse, demand weakens, or the factory becomes underutilized, that same billion-dollar facility can quickly become one of the most expensive assets on the company's balance sheet. The most dangerous fertilizer factory isn't the one that can't produce enough fertilizer. It's the one that can produce 1 million tons, but has to sell them for less than it costs to make them. That is the real economics of owning a fertilizer factory.